Alright, so this is 4.5, indeterminate forms and L'Hopital's rule. Well, we want to be able to calculate limits of fractions whose numerators and denominators both. In other words, if I plug in a for x here, and if I evaluate both of these functions and they equal 0, then this produces 0 over 0, and of course is something that cannot be found. This is what's called an indeterminate form. Other types of indeterminate forms, infinity over infinity, infinity times 0, and so on. So we need to know what we can do when we have something in this form. So L'Hopital's rule, if we go back to the reminder of the definition of a derivative, that's the long definition, not the shortcut, say, well, if I plug in a to both of these functions and they're going to equal 0, then L'Hopital's rule says I can simply just take the derivative of the top and the derivative of the bottom. So let's see why it works. So if I take the derivative of the top and the derivative of the bottom, that's my definition. Next, a limit over a limit is the same as the quotient of this limit. And I can cancel out my x minus a's. This was given that f of a and g of a was equal to 0. So the limit as x approaches a of f of x over g of x is the same as just simply taking the derivative of the top and the derivative of the bottom. So let's see an example of this. If I take and I plug 0 in for x, I see that I end up with this indeterminate form of 0 over 0. And so what I want to do is I want to use L'Hopital's rule that says simply take the derivative of the top, which would be 3 minus cosine of x, and then take the derivative of the bottom, which would be 1. And now this step I look to see, can I plug in 0? And I can, because 3 minus cosine of 0, of course over 1, is 3 minus 1, which gives me 2. So that's what L'Hopital's rule is take derivatives until you can plug in, if you have this indeterminate form, until you can actually plug in your. And then of course I would check it by looking at a graph. So here's another one. If I actually plug in 0, here, here, and here, I'm going to get square root of 1, which is 1, minus 1, which is 0, minus 0 over 2, which is 0. So I'm going to end up with the top 0 and then the bottom 0. So what I want to do then is I want to take the derivative. So the limit as x approaches 0, the derivative of the square root of anything is 1 over 2 square roots of the anything times the derivative of the anything, but the derivative of 1 plus x is just 1, the derivative of the x. The derivative of minus 1 is 0, and then the derivative of x over 2 would be minus 1/2, and then the derivative of the bottom. And so I still cannot plug in 0, so what I would do is I would rewrite this to look a little better, meaning the limit as x approaches 0. I'm going to bring this to the top, so I'll be able to just look at it and use the power rule. So that's 1 plus x to the negative 1/2, because it's square root's the 1/2, but it was in the bottom, over 2, minus 1 over 2 over 2x. Now I'm going to take the derivative again. So if I take the derivative of this piece, I can pull that 1/2 out front. I bring the negative 1/2 down, leave the inside alone, and then I subtract 1. So I get negative 3/2 all over 2. Because this kind of got covered up, that was 2x, and I took the derivative of the bottom. So now I see I can actually plug in 0, and I end up with 1/2 times -1/2. This inside, 1 plus 0, 0, anything 1 to anything power is 1. So I just simply get those two pieces over 2, which gives me -1/8. And the graph of this and see that that does match up. All right, so again, all L'Hopital's rule says is to continue to differentiate my function as long as we get this 0 over 0 when 1 does not become, when 1 is different from 0, evaluating at x equals a, then I can stop. However, L'Hopital's rule can only be applied to limits that give indeterminate forms, the 0 over infinity. So for example, this piece, if I plugged in 0, I'd get 1 minus 1, which is 0, over 0. That's indeterminate form. So I take the derivative of the top, derivative of 1 is 0, derivative of cosine is minus sine, so minus minus, and then I take the derivative of x, which is 1, the derivative of x squared, which is 2x, and now I see I can plug in 0, and it's in no longer indeterminate form, and I get my limit. And I see that this, if you didn't recognize that and you went ahead and you took the derivative again, say you didn't notice that that wasn't in indeterminate form, if I take the derivative of again, cosine x, and then 2, now I plug in 0, notice I get the wrong answer because this was actually not in indeterminate form. All right, if, for example, I have secant x over 1 plus tangent x as x approaches pi over 2. Looking at these graphs, I can see that if I'm coming from this direction, I'm actually heading down to minus infinity. If I'm coming from this direction, I head up to positive. And so I end up, if I'm coming from the left side, I end up with infinity over infinity. So that's in. And so I take the derivative. L'Hopital's rule says take the derivative of the top, secant is secant tangent, the derivative of the bottom of 1 is 0, tangent secant squared. And now I'm just going to simplify this a little bit. So I broke apart the secant. I see I can cancel a secant. I can write tangent as sine over cosine. I can write secant as cosine, and now you see I can, and I actually now can plug this value in, pi over 2, and I get my limit of 1. Same thing, those same steps for the right-hand side, because remember the right-hand side was heading down to minus infinity, and I get 1 rule, the two-sided limit is equal to 1. All right, if I have something that looks like this, I remember that if I could get that sign, in other words, this was a reminder that the limit as h approaches 0 of sine h over h, I remember that that equals 1. And so what I could do is up here, I could let h equal 1 over x, and I could rewrite this limit so it becomes this 0 over 0. And so as x approaches 0, my x, if I solve for x over here, I'm going to get 1 over h, and then times sine of h, which as you can see can be written to look like that. And I get my limit. X heads out to infinity, and as I can see as it's heading out to infinity, I get 1. All right, if I had something that looked like this, if I try to plug in 0, and I try to take the square root of 0, and then I try to plug in 0 here, remember that what a log looks like, the graph of a log, that it never can equal 0. Okay, so I have another indeterminate. If I look at the graph, it looks like it's approaching 0. So what I could do is I could say, well, let's rewrite this as a fraction, meaning ln of x over 1 over square root of x. So all I did was just rewrite that as a fraction. L'Hopital's rule says take the derivative of the top, which the derivative of ln of x is just 1 over x. Take the derivative of the bottom, Now I'm just looking at the bottom, so that's really the same thing as x to the minus 1/2. So I get minus 1/2 x to the minus 3/2. I can rewrite that as the limit as x goes to 0 from the right. I'm just going to bring that 2 up to the top. I'm going to bring my fraction up to the top and bring that x down to the bottom. So all I did was just rewrite it to look and see if I plug in 0, would I still get 0 over 0? And I would. So I could just cancel the x, which might be easier, but let's just go through another L'Hopital's rule, which says I bring the 3/2 down and I subtract 1. That becomes 1. Now I can plug in 0 and I get my limit of 0. As you can see, once again. All right, whenever I have anything with fractions, the first thing I want to do is get a common denominator, because L'Hopital's rule says to make it into one fraction. So my common denominator would just be x times sine of x. This piece needs an x. This piece needs a sine of x. All right, so now basically I've put it into the form of 0 over 0. So let's take the derivative. The derivative of x is 1. The derivative of sine is cosine. The bottom is a product, so the derivative of x is 1. Leave the sine alone, plus leave the x alone, take the derivative of the sine. And I look at this and I see, can I plug in 0 for x? And I see I can't, because if I plug in 0 here, this would be 1 minus 1. If I plug in 0 here, because that's multiplied, I'm going to get 0 plus 0, so it's still 0 over 0. So I just simply take derivative again. So the derivative of cosine is minus sine, and that negative makes it a positive. The derivative of sine is cosine, and now I have another product. So the derivative of the first one, leave the second one alone, plus leave the first one alone times the derivative of the second one. And now I see if I plug in 0, so let's just start plugging in 0, I'm going to get sine of 0 over cosine of 0 plus, that's just 1 times, cosine of 0. And this is going to be plus 0 times minus sine of 0. And so as I can see, this piece right here becomes 0. This piece right here becomes 1 plus 1, 2, that becomes 0, or my final answer of 0. And certainly as I look at the graph, I see that that makes sense. As x is approaching 0, my function is approaching. We also have indeterminate powers, which are things like 1 to infinity, 0 to 0, infinity to 0. So what we can do is we can actually take the log of the function and then we'll undo it. So if I take, and in this case I'm going to use natural logs, remember the inverse, I could undo it by using this e to whatever power. So I take the log, I apply L'Hopital's rule, and then I exponentiate to do here. Take the log of the function and get my limit by using L'Hopital's rule, then get my original function, because in other words this is the inverse, by taking e raised to that actual. So if I have something like this, then this is my function, my f of x, so I can rewrite this as the limit as x approaches 0 of ln of 1 plus x to the 1 over x. And then by my log rules, I can actually take, let me write my limit as x approaches 0. I can take this 1 over x down, so I'm going to have 1 over x times ln of 1 plus x. Well, notice I could rewrite that as a fraction as ln of 1 plus x over x. This is still in indeterminate form, because if I plug in 0, ln of 1 is 0, and then of course in the bottom would be 0. So I get the derivative. The derivative of the top is 1 over 1 plus x. The derivative of the bottom is 1. Now I can plug in my 0, and I get my limit of 1. Now remember, this is the limit. So what you need to do is and I already give you the answer. The definition, I got 1, but my actual answer is e to the first power, or e, or as you saw in that last graph, about 2.78.